So in this question, we're asked to show that the pressure P can be shown by this equation here that's given to you. So to show that question, and we're given that rho in the equation is the density of the gas, and capital M is the mass of 1 mole of gas. Now, we're given this original equation here, so this is what we need to work from, obviously. Now, the first thing you're going to want to identify is what you want to remove from this equation here and what you need to replace it with in here. So, first thing we're going to look at is the volume. Now, the equation you'll be familiar with is that volume equals mass over density. And as luck would have it, density is one of the variables that we want to remove to place in the equation here. So I've written out this equation, V equals M. Now you've got to remember that this is a lowercase m because this is the mass of the whole gas, not just 1 mole. And that's over rho, the density. And this actually gets you your first mark. So that's the first part done, and now the second variable we need to replace is this little n here, which means the number of moles of gas. Now, the only other variable that we've got that we need to replace is this capital M here, which is the mass of 1 mole of gas. So, I've written down here that the number of moles is equal to the total mass divided by this capital M, the mass of 1 mole. So now you've actually got all you need to answer the question. All you need to do now is substitute these two equations, which actually get you your first 2 marks already, into the original equation that you've got up here. So we just write down the equation and then replace V and N with the 2 equations that you've got at the top. You can actually have these in any form, but I think it's easier just to have them with the things you want to replace as the subject of the equation. And then rearrange this. You'll notice that the little m's cancel out, and you can bring your density rho up to the other side, which gives you the equation in the form that's asked. So this is D part 1 of the same question, and we're being asked to calculate the density of the air at this height. Now, in the last part of the question, we generated this equation here, which actually links the pressure, the density, and the temperature, which we're told at the top of this question are the things that will change with the height. So the first thing I've done is looked at the proportionality between these variables. Now, the reason I've done that is because this R here and this M for this particular equation are constant, which means that if I write it in this form here, I don't need to worry about them as much. So, because we've got this link of proportionality, I've then been able to write down this link right here, which is the pressure at the top, which is indicated by this little t here, over the pressure at the bottom, which is indicated here, is equal to rho little t, t little t, which is the density at the top and the temperature at the top, divided by rho b TB, which again is the density at the bottom and the temperature of the bottom. Now, something important that you're going to want to remember is that your temperatures are actually in degrees Kelvin, not degrees Celsius. So they've given you the temperatures up here. So at the height of 8,570 metres, the temperature is minus 33 degrees. So you're going to want to change that. And the temperature at sea level is 20 degrees. And just remember to add 273, and it's just that simple. So we sub these values in, along with the density that you're given at sea level, which, looking at the text, is 1.3 kilograms per metre cubed. Now, the trickiest part of this question is actually looking at the pressure. Now, from the text you're given that the pressure at the height of 8,570 metres is 0.35 times the pressure at sea level. So I think the easiest way to actually look at this is as I've written down here. Now, it shows here that you've got 0.35 P over P, which is just this bit here, the pressure at the top over the pressure at the bottom. And now as you can see, the p's will just cancel, which actually just leaves you with 0.35 as is written here. That's the easiest way I think I can explain that. So now you've got your equation with all your values subbed in. All that's left to do is just to rearrange the equation, just bring values on the bottom over here, up to the top over here, times them by 0.35 as is done on this top row, and then bring the 240 down to divide, and you're given your answer of 0.56. So in this last part of the question, we're asked to determine the ratio. That's the number of air molecules at the top of the climb in this guy's lungs and the number present at sea level. Now, one of the important things to know is that we're now looking at the number of molecules, not the number of moles, which means you have to change this equation, PV equals NKT. So as you can see, I've done the same thing as I did in the last question and looked at the proportionality to get rid of my constants, so I don't have to worry about them. So that's the V and the K in this case. Now, so what this actually gives you, if you move this T over onto the other side, is that N is proportional to P over T, so that N equals P over T is actually a constant. Now, what we're going to do is, because we need to divide the numbers, I've written this out over here. We have the pressure at the top divided by the temperature at the top divided by the pressure at the bottom divided by the temperature at the bottom. So what you're going to do is, because this is dividing fractions, this second one here flips and you end up with this over here, which is NT over MB equals PTTB over PBTT. So all you do now is just sub in the values that you've got from the previous question and bob them in your calculator, and there's your answer.